That's it. So yeah, please go ahead. Thanks.
So hello everyone, and just to check if you have my screen. Okay. First I'm gonna introduce myself briefly, and then we will go over the code. I'm Shukufa. Currently I'm a master's student at University of Calgary, under supervision of Dr. Farhad Maliki. And I work in Vision Research Lab. We focus on developing deep learning-based models and work on mostly specifically on medical data. And one of the tasks we do is just segmenting the medical data, and this is what we are going to focus on this week. And I also currently I'm a machine learning developer at AltaML company. So nice to meet you all. Let's go through the code. First of all, I want to give you an overview about the project, about the assignment that we had for this week. So if you take a look at the assignment, you have realized that it is a segmentation problem. We are going to segment the left atrium chamber of human heart. And the importance of this problem is that this segmented part can be used for professionals to just measure the functionality of heart and the volume of chambers. And so that's why these problems are important. And through our code, we're going to create an automated system for segmenting this chamber. And the data that we had for this assignment was 20 annotated MRI images of left atrium chamber, and it was extracted from Kaggle website. I can share you the link for this Kaggle later. Then, and yeah, you can just read more about the data here. And so if you saw the dataset, you would see that it is a 3D images dataset of volumetric data. So since there are only 20 of them, it shows that we have a very small dataset. So to increase the number of our data to work on, we just converted the 3D images into 2D images. And for the volumetric data, we have 3 different views, and which you can see axial, coronal, and sagittal, which is just processing the volumetric through different views. And I just want to show you here. So for example, you can see we are looking at the volumetric data from this view. This is the sagittal view and coronal view. So for our case, we are working with the sagittal view. And for the model that we have used, just please ignore the bottom border. We built a model from scratch, which is a unit model. It has 4 downsampling and upsampling blocks, and they are connected with convolution layer and flexpooling. And we have transport layer at the upsampling. And finally, we also have skip connection that is passing the low-level information from the very first layers of the downsampling to the upsampling block. And also, we are going to use a pre-trained model and leveraging from transfer learning, which was the topic for this week. So by that, let's go through the code. Okay. First, we are running the initial setup and installing the required libraries and installing the Python modules. Through segmentation models PyTorch, we are going to just use the pre-trained model that we have later. So I just run all of them before, so it's because of that matter of time. I run them before. So through this code, through this instruction, you are connecting you're mounting your Google Drive to your Google Colab, and you can put your dataset file into wherever you want in your Google Drive, and through this you can unzip it into the destination folder, into a desired folder that you're gonna use. Just need to keep this pass it for reading your data later. And here we are defining the dataset class. It's a cardio, and it is inheriting from the dataset class of Python. We are just doing the initial things. We are applying the initial processing and pre-processing on the volumetric data. As I said, we are going to convert the 3D images here to 2D images, and we make sure that these labels and images, 2D labels and 2D images are mapping together. And since our problem is segmentation, by the labels, I mean the masks that we have for the part we are going to segment, which indicate the left chamber. And okay, yeah. And through the get item, I just applied the transformation that we have, which are some augmentation techniques that I define here. It's just flipping and rotating data. We apply these techniques to just increase the number of our data set, and just just to try our model to learn better and see improve the generalizability of our model. So okay, here I'm calling the cardio data set and passing the correct path for the train, validation, and test. And I just set the transformation, the augmentation techniques that we have here only for our train data, and I load it into train data, validation, and test. So here I'm gonna just visualize a sample on our data set. You can just get the length of our train data. As I said earlier, we have 20 of annotated MRI images. I considered 18 images for the train data and 1 3D image for validation and 1 for test phase. And if I just convert this 3D into 2D, I have around I think around 200 of 2D images for each. So yeah, here I wanna run it again to show you. It's just applying whenever I take a sample from the dataset, it applies one of the techniques that we have for augmentation. Here, this is the corresponding mask for our image. I can run it again, and you will see that, for example, it is the same image, but since it's applying different sets of augmentation, it just changes. But the important part is that the mask is also changing with the corresponding image, and it means that the augmentation is applying on both image and the mask. You can try it later and run it again and again for different samples. And I'm just loading my data into their corresponding data loaders. I just defined a batch size of 32 and made the shuffle through for the training. And these are the number of workers that help the training our model faster. So this is the initial model that we had, like the base model, and we just built it from scratch. And as I showed you the architecture in the picture, it has 4 blocks. For encoder, you see we have 4 blocks, and for the like upsampling. We have also fault blocks. They're connected with convolution layers and max points. You can later get into more details about the architecture of our units. But since we have data, as you can see, we don't have any colorful images. So the input channel and output channel, which would be the predicted mask, are both in grayscale. So the number of inputs and output channels would be 1. So we feed it here. I think this was the to-do task you had. You need to just call the name of the class and just pass the number of input and output channels. And here we are creating a binary cross entropy loss function for calculating the loss, and the optimizer is selected as Adam is selected as our optimizer. We can change the learning rate, and yeah, for the evaluation metric that we have to just calculate the accuracy, it's more common to use IOU, which is the intersection of union, for the segmentation tasks, and the division of that is here. Yeah, and through this, I'm just setting our running machine to GPU to make the training faster. And I think you had the 2 parts for the validation phase. We had training phase, which is completely similar to the validation phase, but here, through this, after we are defining, for example, the number of reports here is 35, and for each batch, we are iterating through all of the images and masks and feeding it to the model, and just calculating the loss and using the optimizer to fill the process backbone. And after each like a batch, we are just calling the evaluation to just pass that validation data and passing our model that we have and device, and these are the settings that we can have, the parameters we're gonna pass to the evaluation method. Evaluation method, and it is completely the same. The difference is that we are setting our model to the evaluation phase, and we set the torch.nograd to just prevent our model from learning the validation data. It's just preventing the model to get updated when it is encountering with the validation data, and we are not going to learn this data. It's just learning through the training phase. Yeah, the only difference is here, and I run it with the base models that we had. Here you can see the name that we defined for our unit is just model. And after running, I just run it for 11 epochs because it took longer. If I wanted to continue until 35, but you can see it starts from a high accuracy, but it's kind of a stock. It's just the accuracy, and that's values for training and validation at the same time. It just stocks at the accuracy around 40%, or it can get higher to 50%. Later I will show you the graph for that. And so here, to just improve the performance of our model and the accuracy of segmenting these chambers, we are using a pre-trained model which has in the architecture of the encoder part is the ResNet, and we are using the weights that were like pre-trained on the ImageNet data sets. So this would define our pre-trained model. The number of channels again is 1 and activation is sigma. We are defining our optimizer based on this pre-trained model. We still have binary cross entropy for calculating the loss. And again, we want to train and validate our data using this pre-trained model. So for the model that we use is just the pre-trained model, and we have the same code that we had for the model, for the unit model, just calling the evaluate and passing the validation data and the pre-trained model to train it on, to test it on the validation data. So for this pre-trained model, it starts from lower accuracy, but you can see it is getting higher and higher, which it's like it's getting higher with faster speed, and it's just achieving the accuracy of around 80%. And if I continue the training and training phase, I think the accuracy would go like around 85%. And just to test it on the test data, you just need to call the evaluate for the test data loader and see the accuracy. I didn't run it because I ran the pre-trained model, but if you just like it yourself, you will see that the accuracy for the test data loader would be much higher compared to the to our base model, which was UNet. I will also show you the analysis that I had myself. Okay, so this is the care for the accuracy for unit model. It starts from the higher accuracy, but it's stuck around the accuracy of 50%, 55%, I think. And for a pre-trained model, the number of epochs after 60 epochs, it gets into the accuracy of 54%. But for our pre-trained model, it is much faster. And after only 35 epochs, it gets into high accuracy of 87%, for which the curve is come here. And yeah, I also continued learning our model. You can see here, this is the ground truth of our data, and this is the predicted mask using the pre-trained unit model. It shows that it is it is highly accurate. And I just stack all of these 2D predicted images on top of each other, and I formed a volumetric mask, which can be seen here. The actual volumetric mask that I had was this, and the predicted mask had the shape of like this, and I just merged these two versions to see the difference, and it shows that it has a high accuracy. So that's it for today. I think I can stop sharing my screen, and I can answer to the questions that you might have.
Thank you so much. So the solution to the assignment, I saw that the assignment has a few tasks at the very end of it as well, like the to-do tasks. Will you provide the solution to this afterwards?
Sure,
Like
yes.
the notebook with the solution? Great.
Yeah.
Thank you.
And yeah, I will share the link of Colab. I wanted also share the link for the dataset that we have. It was from Kaggle website.
There's a question from Trank. Which one? So Trang is asking, when you perform transformations in cell 4, do you look at the images first before deciding what transform that you will do?
Yes, I think it's good to first just take a look at your data that you're working on. For example, if your data set is something, if you also you need to consider the task that you are working on. For example, if you have a classification task, maybe this set of augmentation techniques that you wanted to use would be different. But for our segmentation, since we are trying to mask a specific area, it's good to just play around the shape and the rotation and the flipness of our images. So these are the sets of augmentation techniques and transformations that we can apply for the segmentation problems.
I see that a few people just joined, but the tutorial has ended. It's kind of fun. So yeah, does anyone else have any questions? I will definitely like post a YouTube recording. Let's post this recording on YouTube, and you guys can view it later. And both the data and the Colab is on the Google Drive. That is not on Gumroad. I can share it again. Well, and then the solution to the assignment, like Shikufa will send a document with like solution at the very bottom as well. If no one else has a question, we can end this tutorial. It was a very quick one. So thank you guys for joining, and thanks again to Shikufa for preparing the material.
Thank you, everyone. Have a good day.
Recording.